Hey there. Okay, so this problem, a sample of drinking water was tested for lead 2 plus. It was found to have a lead 2 plus concentration of 17.46 pp parts per billion, ppb. Uh, a 9 milliliter sample of that drinking water was then spiked with 1 milliliter of 2.28 uh, parts per billion lead standard. The analysis of the spike sample gave a concentration of 15.94 parts per billion of that lead. So find the percent recovery of the spike. Okay, so there's several parts to this problem. You're going to have to figure out well, first off, you're going to need the formula for percent recovery of a spike. That formula is right here. Once you have the formula, this actually becomes a lot easier because the formula is pretty explicit. However, there is a caveat that people get tripped up on. So first, let's look at the formula. Percent recovery, that's what you're looking for. Remember, it will be a percentage, so it has a times 100 here. That's going to be the concentration of your spiked sample, so the one that the spike was added to, minus the concentration of the on-spike sample, so that would have been the tap water at the beginning. Drinking water, my bad. I don't know if there's a difference there, but yeah, drinking water at the beginning. And then that'll be divided by the concentration of what you added, which again you have right there. So note though, you do not yet have the concentration in your spike solution. It didn't give it to you. It gave you everything you need to get it, but it did not yet give it to you. And so what we need to do is we need to get that concentration of your spiked sample. Then we'll have all these concentrations put in. You should note this calculation right here. The reason these are used as concentrations rather than part per billion, percent, or anything like that is that as long as these are relative concentrations, they'll work. So you could use like milliliters in all these, or molarities in all these, molalities in all these, as long as it's a relative concentration, it would be fine. Anyways, we're going to have to get that concentration for the sample after it was spiked. That sample after it's spiked, that's going to have a combined volume that's this value right here. And so that's that 9 milliliters that you saw right here was spiked with 1 milliliters right here. And so that gives you a total of 10 milliliters after you've put these two things together. And so you're going to use the dilution equation, which you probably remember from Gen Chem, where C is your concentrations. You have concentration at state 1 times the volume at state 1 equals the concentration at state 2 times the volume of state 2. Note that as long as your concentrations and volumes have same units on both sides, you are good to go. And so you now plug these values in. You start off with that 17.46 times 9 milliliters. That would be your initial drinking water solution. It was diluted down to 10 milliliters. So your on-spike sample of this is going to be diluted down to 15.71 parts per billion. That's just the dilution factor. That's how much lead carries over from that drinking water. Okay? Well, the other part of that sample is going to be the stuff you added, the spiked sample. Okay? And so this will be the concentration of the stuff you added. It's going to be 2.28 parts per billion. That's what you added. You added 1 milliliter of it, and it has a total volume of 10 milliliters. So you multiply these, divide that over, and that gives you your number, concentration of what you added. And then finally, it had the concentration of what it was actually tested for. I hate this website sometimes. Okay, anyways, this is the concentration of what that spike sample is. Okay, and so Now you have calculated what portion of it comes from that original drinking water. And remember, it is diluted, so you've taken that into account. You've recalculated it for its dilution. You then have figured out how much of that diluted sample is from your spike, what you added. And then finally, you have the actual measurement of that sample. So you plug it into your formula, spike sample here, the on-spike sample there, that's the small number, that is the stuff you added. These are the numbers right here for my problem I'm looking at. And you'd subtract those, you'll get a small positive number, it'll be divided by this, and then multiply 100 to make it a percentage. And so that'll give you 77.7%. I think this is actually pretty easy once you realize that you need to do the dilutions. That's typically where problems occur for the students, is that a lot of students would take these numbers here and don't think about the fact that you've actually diluted these numbers because you've added only 9 milliliters of this out of the entire 10, right? So it's a dilution. And same thing here. So to get those dilutions done, plug it into the formula, and that should do it. Let me know if you need me to work it out more, if you don't understand anything. I sort of went over this pretty quick because I think that it would be a difficult thing overall.